Jan is a research associate at the University of Cambridge, and he's really a sought-after speaker. I realized quite recently, SpeechBrain, which is a very well-known speech recognition library, had their main event co-located into speech. And so they were looking for folks who could speak on a variety of different types of topics. And they invited Jan actually to speak about self-supervised speech in the context of federated learning. And in that area, Jan is literally one of the world's leading experts. And so I'm really happy that Jan could find the time in his schedule today to present some of his work and ideas in this area for us. So with that, over to Jan. Thank you for being here with us today.
Yeah, thanks, Nick, for the invitation and the introduction. So let me share my screen. Great. Yeah. So in this talk, I will look into the topic of the federated self-supervised learning for speech. And obviously, it's a combination of federated learning and self-supervised learning. So I know you may not familiar with one of them. So to better understand this topic, let's just break this topic down and introduce them separately. So first, what's the speech self-supervised learning? So let's take a look. The self-supervised learning is a form of unsupervised learning, and that means we don't need the labels for training. And instead, we generate the labels from the data itself and design the task that the model can learn the useful representations from this process. And when applied for the speech data, the speech self-supervised learning focus on using the large amount of unlabeled audio data to learn the representations, and that could be used for various downstream tasks. So basically, the self-supervised learning, the SSL for speech or another type of data involve two stages. So at the first stage, the encoder of the SSL model extracts the self-supervised features from the unlabeled audio data. And then the pseudo labels are generated based on the specific SSL objectives. And this could be used to calculate the SSL loss and update the model weights. And at the second stage, the pre-trained SSL encoder can be used to solve the downstream tasks by adding a downstream model on the top. And during this fine-tuning process, the SSL encoder can be frozen or not just based on the requirements. And as for the speech-related downstream tasks, I think in almost involved all of the common tasks like the speech recognition, the keyword spotting, emotion recognition, speak identification, and so on. And yeah, just as Nick mentioned, in practice, a study of the speech self-supervised learning has gained much attention in recent years. So this figure just shows the number of occurrences of self-supervised concepts at the Interspeech conference over last 5 years. And obviously, the research related to this topic become extremely active in the last year, if you see the figure. And the reason why this topic is so popular is that it's really work well on the different downstream tasks. And if you see this table, compared to the traditional features like FBank on the top, the large-scale SSL model on the bottom have got the new state of performance on almost all of the downstream tasks, right? Although the SSL perform well on speech and audio data, on the other hand, this kind of model are huge with hundreds of million parameters, and also they are hard to train and resource incentive. So for example, to gain a state-of-art performance with the Wave2Vec2 model, so which is a state-of-art SSL speech model, you have to burn your GPU for thousands of hours. And of course, this is not good for our environments. Yeah. So okay, yeah, let's see the next topic, the federated learning. I think most of us are familiar with this topic, so I just quickly go through it. Yeah, so FL is a form of distributed machine learning scheme, and the training data remain on the devices. And this approach is to solve the privacy concern of sending the raw data to the centralized server. And the typical FL procedure have the following steps. So first, a global model is initialized on the server, and then a fraction of the clients are chosen, and this receive the copy of the global model, and the clients perform the local training using their own data, and then send the updated model to the server. And on server, we do the aggregation to get a new model, a new global model. And this process is repeated for a number of rounds until the model converging. Yeah, and unlike the centralized training, there's more constraints when training the data on the devices. And yeah, and the core challenges of federated learning are divided into 4 aspects. So first, it's mainly due to the limited communication. It's mainly due to the limited resources on the device. For example, like the bandwidth, energy, or power. And second, the storage and computational and community ability of each edge device in the system, in the federated system may differ. And also, the distribution of the user data would be very non-IID, so which would cause some issues for the training. And also, lastly, as the main concern in FL, the privacy could be protected, by the only sharing the model updates instead of the raw data in the training process. However, the user's sensitive information may still be reviewed during the communication between the devices and the server. Yeah. So okay, after we understanding the main characteristics of SSL and FL, so let's just go back to the original topic, the federated self-supervised learning for speech. So why do we want to combine these 2 concepts, and what benefits can we get if we combine them? Yeah, actually, FL and SSL have many complementary features. So for example, the FL can offer almost infinite data from the user side, right? And the SSL could benefit from the large-scale data training, so it matches. And also, the user data is almost unlabeled, and the SSL doesn't require the labeled data for training anymore. And on the other hand, as for the privacy, so we can't say FL offer the privacy guarantee, but it indeed reduces the risk of the data breaches and also provide the opportunity to make use of the user data for SSL model training. And at the last point, FL have millions of devices, right? And which could jointly provide the large compute capability required for SSL, right? So as a result, combining SSL and FL feels natural. But is it easy to achieve that? Yeah, so we actually have several concerns when combining them. So for example, from the hardware aspects, the FL devices may not afford the large SSL model training, as these devices only have the limited compute capabilities and memory. And from the algorithm aspect, the no ID data and the heterogeneous the data availability in FL may destroy the SSL training. So to investigate the feasibility of the speech federated self-supervised learning, we can set up some experiments. And here we just use the Wave2Week2 model both its small and large version to run some benchmarks. And for the data set, we choose the Common Voice Italy set as is relatively small. And then we choose the several devices for the benchmark. Here we choose the A40 GPU to represent the centralized training. And as for the edge devices, we use like the MacBook Pro, the Raspberry Pi, and Jackson XVR AX, AGX, and so on. Okay, so we first conduct an investigation about bottleneck that cause the SSL model to be expensive to train. And to do this, we just break down the wave-to-wake model into 3 modules. So which are the CNN module, the transformer blocks, and quantization module. And this table just shows the number of parameters and the flops for these 3 modules in wave-to-wake 2. Yeah, and immediate observation is that you see the transformer block is the heaviest module compared to the rest. But we need to keep in mind that this analysis doesn't consider the training dynamics. So next we have in-depth look into the linear level in terms of its memory and the compute. Yeah, so if you see this figure, so each bar in this figure represents 1 layer, and starting from the first layer to the last one over the x-axis. And we can see that and at the end of the forward path, the memory concept is at its maximum. So it's showing in the red cross in the figure. And an interesting observation is that you see the high memory cost and compute needed for the CNN encoder stands out compared to the rest of the model. So this mainly due to the consideration of the size of the input tensor passed through the layers. Okay, so now we have known the bottleneck of the SSL model, and let's put it into the real FL environments. So let's first see the memory consumption. So this figure shows the memory cost of training or the wave-to-wake base model and large model on different lengths of input sequences. The typical FL devices like just Jackson XVR AX or Raspberry Pi have only 8 GB memory, and you can see the lower horizontal dashed line, which is the 8 GB line. And on the other hand, some more powerful devices like XVR AGX or the Snapdragon 817 has a 16 GB memory, so which is showing with the upper dashed lines. Yeah, so from this figure, we can easily see that device with 8 GB can only train the base model, the small model, and the device with 16 GB can use the large model with a sequence of 7 to 8 seconds at most. However, if longer sentences, for example, the 15 seconds are considered, because it's a typical case with current SSL model, all of the devices could only be able to train the base model or even none of them. Okay, so next, as for the training time, it's also important for us to this table and shows the average seconds per batch of the wave-to-wake model if using the sequence of the average length 5.5 seconds. And yeah, so you can see some OOM here. So it stands for out of memory. And obviously, the FL device are dramatically slower than the GPU. So for example, the voice case, the Raspberry Pi is around 200 times slower. And we noticed that the use of the mixed procedure can provide a boost in the training speed for the device, but the support of the mixed procedure training is currently rare in the embedded devices. So if we consider a full FL training, the A40 GPU would take around 3 days, so which is obtained from the real experiments, and then the FL device would take like weeks or even months to finish the training. So as a result, the current large-scale FL SSL training is simply impractical for the current real-world FL environment. On the other hand, what if we just ignore the hardware constraint and run the SSL training in FL with the current algorithm? And would it be working? So let's set up another experiment. Here we just use the same model, the wave-to-wake2 and the common voice Italy set. And basically we have two FL partitions, the 10 clients and 100 clients FL. And we also investigate two aggregation methods, the Fed average and loss-based aggregation. And the loss-based aggregation just weighs client's model based on the average training loss of each client. And as for the training, the downstream task, we choose the ASR, it's speech recognition, and add 3 linear layers on the top of the SSL model. Let's see the results. So we can see that all the federated SSL representations provide a competitive performance in both FL scenarios compared to the centralized setting. So this shows that the feasibility of training SSL model in FL if hardware is unconstrained. And also, if you see the loss-based aggregation, which achieve a lower word error rate, so lower is better in the both FL setting. So this indicates that if we're reducing the effects of the low quality clients, which could help the aggregation process in the federated SSL training. Okay, so overall, so based on our analysis, the hardware constraint becomes a bottleneck of training speech SSL model in FL. And hence, we need to think about how to solve this issue. And of course, a more efficient SSL method is required. And also, the better aggregation strategies are also needed to speed up the SSL model converge. And so it's still a long way to go. And of course, please come and innovate with us. So you must be curious about implementation. So here it's easier to run the simulations of speech federated self-supervised learning by just integrating the flower with speech brain. So speech brain is just a popular speech toolkit. And also you can just look into the details of how to combine them on the tutorials, so which is on the speech brain and the flower website. Okay, so that's all. Thank you for listening, and feel free to ask questions if you have any. Thank you.
Thank you, Jan. It was a great talk. Let's see if we have any questions from the audience while we wait a few minutes. I'll ask a couple. One question would be, how interested are speech researchers in federated learning right now? There's a lot of papers being written in federated learning, a lot of papers being written in speech, certainly. But is this a topic area that's really taking off, or is it still yet to be discovered by many of them?
Right. So I'm mainly working on this topic of combining the FL in speech during my PhD study. So, and as I noticed, there's more papers related to this topic from like last 3 years. And I think it's getting active. If you just check in the main conference of speech, like the interspeech or ACASP. Yeah.
I guess just along those lines, how easy is it for someone to use Flower and SpeechBrain together to do these types of experiments? Are there, is it a fairly well understood path, or what's it like to do that?
Yeah, I think actually it's easier to combine these two toolkits. Yeah, just due to it's a friend, both the toolkits have the friendly API. So, for example, if you want to do some speech related training using the speech brain within Flower, you can just replace the original training function, in the feeds function in the Flower framework with the speech brain training function itself. And I think also we need to replace the data line as well to read the data. And after that, it's just we can start the FL training. It's
I
not
see.
Yeah.
We have a question, and it is asking, how much performance improvement do you expect?
So sorry, I'm not sure what do you mean about the performance improvement.
I suppose from using FL or not using. I guess you have a choice. You can use it or not. How much of a gain would you expect to see?
Okay, I see. Yeah, actually, currently there's no clear paper stating that how much performance I can get from the FL. We can't get the real user data to do the experiments. But I'd like to say is it has a real potential to gain the improvement if we using the user data, because it's almost unlimited, and also on the other hand, the SSL model benefit from the large scale data set. So yeah, but on the other hand, one thing you need to keep in mind that the centralized training commonly better than the FL training. So how much more data we needed for FL to beat the centralized training is a research question that's unsolved, I think.
I see. Interesting. Yeah, we have one other question here. It's asking, what is the most common experimental setup that you do with speech in FL? I guess they're talking about what type of data set and so on. But what do you think is really representative of what can be done?
Oh, okay. Yeah. So if you considering a specific task, for example, the speech recognition, I think for data sets, many existing people just doing FL training on the library speech data sets, and also the Commonwealth data sets. The Commonwealth one is more, I think it's more fit to the FL training because it's containing more users, and also just more realistic. And if you're considering the SSL training, self-supervised training, the library speech is also an option. And actually, there's no paper doing speech SSL training in FL because it's already, just as I mentioned, it's really resource intensive, and it's harder to achieve. Yeah.
Right. Makes sense. And one last question, let's make this quick. It is, what's the MNIST equivalent for a FL and speech example? So it's similar to what we were just asking about. But what is the MNIST? MNIST is well known to be like the simplest thing. You don't need any GPUs and so on to run, but it's still a somewhat meaningful experiment to run. certainly many people know about it. And
Mhm.
so what is the MNIST equivalent for the FL and speech setup? And in other words, something that's easy to run that you don't need even GPUs for to get a result from.
I see. Yeah, I think for this question, we also need to consider what type of task we want to train in FL. So I guess the simplest task related to speech is the keyword spotting. Also, it's just if a very common data set for that is it's called speech comment speech command. It's from Google, and I think it's easier to train to get and the model for that is small, so it's good and it's a good one to start with. So if you want to train some FL plus speech examples, and of course, if you want to train like a harder task, for example, the speech recognition, I think there's no easy task, easy data set to do that, because even in the centralized training, it takes of a certain GPU hours to finish the training, and for FL it will take longer. Yeah.
I see. Cool, great. Well, thank you again for the talk. It's a wonderful area to be exploring. And so thank you for showing us a bit about the space. And I hope many of the community out there decide to join you in this exploration.
Thank you.
Great.